So, we will continue from the last module's problem solving, which is we wanted to look into two cases. That there was a silicon device that was dissipating about 600 watts, and two teams were working with different solutions how to dissipate the heat so that the junction temperature is kept below the maximum allowable, which is about 100 degrees Celsius. So, and also there is a restriction that the temperature rise on the flow side should not be more than 10 degrees C, with inlet being at 47 degrees Celsius. So, in the last module we saw that team A worked towards the having fabricating microchannels on the silicon device directly, so that they eliminate additional resistances in the form of spreading resistance, conduction resistance, and so on. And so, the team B on the other hand decided to put an extra copper block and spread the heat over a larger base. The silicon device by itself was 30 millimeter by 30 millimeter, but when the team B they chose to put the copper block on top of it, and the copper block makes contact with the silicon device using a thermal interface material. So, they are introducing additionally 3 additional resistances on compared to the silicon team, that is team A. So, here again the microchannel dimensions are the same. The only thing is that the overall surface area has been increased. So, we will see whether team A's solution is better or team B's solution, and just to recall, from team A solution was such that the heat sink directly integrated on the silicon die. So, with that the resistance that was calculated was this, and so the T junction based on the inlet temperature was calculated to be this. So, now we look at team B solution. So, here we have on top of the copper, on top of the silicon, there is a conduction in the silicon, there is R TIM, and there is spreading resistance, and then this is the convective heat sink resistance. So, these additional resistances show up compared to the previous case. So, the TIM resistance is something that is given. So, we can use that value of 0.056 degree C per watt. The spreading resistance, using the formula we discussed previously, is also known or can be easily calculated, and it is found to be 0.047 degree C per watt. And the cold plate or the heat sink resistance that was enabled on the copper can also be calculated. The only difference is that we use the same relationship 1 by m dot CCP 1 minus exponential of minus H A by m dot C. So, this H is already known for both the cases, it is 8000 watt per meter square Kelvin, but the area is the one that changes here. Since the copper base is 60 mm by the flow length is 60 mm and the width is 75 mm, which is much higher. It is more than twice compared to the area of the silicon device. So, we need to include this here, and we need to calculate a surface area based on the same as before, which is there is a spacing bit, a channel fin is 0.5 mm thick and the channel is 0.5 mm thick. It is very similar to before. So, with all these calculations, with all these numbers and m dot from previous, we can easily estimate the cold plate resistance or the heat sink resistance to be 0.027 degree C per watt. So, the total resistance from junction to the ambient turns out to be a combination of 0.056, ignoring the resistance offered by the silicon, spreading resistance of 0.47 plus heat sink resistance of this, we get a total resistance from this, and this if you use to calculate Tj, it happens to be 94 degree C using a 47 degrees Celsius ambient. So, it is seen that in this case, depending on the severity of the power, it may be better if the power is very high power is being dissipated. It is probably much better to spread the heat to a larger base, use this larger surface area to dissipate your heat than just putting it on a silicon level, which is a smaller size. Even though water based microchannel cooling is very effective, it is best not to, in many occasions it is better to spread it over a larger area and then dissipate it. So, with this we conclude this problem and move to another problem, and this problem is of interest when someone is trying to design these PCBs, these printed circuit boards, and trying to figure out what should be, where should we place a component relative to the processor. Let us look at this example. The question that we are talking about, or this problem, is that we have a printed circuit board and there is a heat source or a chip, whatever you want to call it, and then it is mounted with some heat sink. This is the TIM interface and this is the silicon device and this is your heat sink. All the necessary information for TIM, silicon, everything is provided, but the goal of this problem is, as air flows from right to left, a new component needs to be placed in the board. The question is whether to place the component, the new component, here or here is the question. So, should we place the component before the processor, high power processor, or should we place it after the processor? That is the question that we are trying to answer in this. The high power processor, that is this is called the processor, and let us call this some low power device, LPD. So, the processor power is about 150 watts. The airflow comes in at 21 CFM. Typically, many manufacturers use this mixed units, not many use the SI units. CFM stands for cubic feet per minute. So, this needs to be converted to meter cube per second before it can be used for our calculations. And the processor, this dissipates 150 watts and it has a junction to case, that is from here to here, resistance of about 0.1 degree C per watt. And the thermal interface material associated with the processor dissipates is about 0.108 degree C. The maximum allowable case temperature, that is this temperature we will call it, is 85 degrees. This is the max. So, anything that exceeds 85 degrees C means we have failed in terms of protecting the processor, and so we need to ensure that the processor is well below this 85 degrees C at the case. Then the heat sink resistance, in order to calculate heat sink resistance, there is a effectiveness of the heat sink, processor heat sink is given, and it is given to be equal to 0.55, and it has no units. On the other hand, the power, the low power device dissipates about 48 watts. But this low power device has a maximum allowable junction temperature of, it can handle much higher temperatures. It has a maximum allowable junction temperature of 120 degrees Celsius. And the low power device has a convective conductance of heat sink conductive conductance of degree C per watt, and again the thermal conductivity of its interface material. The low power device also comes with, if this is the low power device, it has a thermal interface material and a heat sink sits on it. So, the convective conductance, which is H times A, is given as 1.36 watt per degree C. So, this is given, and from this we are expected to calculate the, we have to identify whether it is better to put the low power device upstream of the processor or should it be placed downstream of the processor. That is the question we are talking about, and air is given as the flowing medium. The thermal interface material associated with this thermal resistance is also provided for our calculation. So, let us first look at, this looks like a seemingly simple problem, and one may wonder, the power is small and also the junction temperature is higher than the processor junction. The junction temperature for the processor is lower compared to the junction temperature of the low power device. So, it may allow the low power device to be kept before or upstream of the processor, so that first let us get rid of that power to the air, flowing air. But it is not a trivial question, and so we will just look at it one by one. First, the CFM, that is volumetric flow rate, is given as 21 CFM. So, if you use the conversion, units conversion, and calculate a mass flow resistance, mass flow rate for this, it is approximately 116 kilogram per second. So, we are already provided for the, let us first calculate for the low power device. So, the effectiveness of the low power device can be calculated. The effectiveness of the heat sink that is sitting on the low power device is nothing but 1 minus exponential of minus HA, which is the U of the low power device that is given in the problem, and m dot C sub P. And if you use the values and calculate the effectiveness of the heat sink that is sitting on top of the low power device is only 0.11, and if you go use that and calculate the low power device heatsink resistance, then it turns out to be 1 by m dot C sub p times L by D is equal to 0.11. Since the processor, on the other hand, this is the heatsink resistance, the effectiveness is already given for this processor and this is given as 0.55. So, the heatsink resistance for the processor can be easily calculated using the same relationship, but substituting for the processor we should be able to get that. So, first let us look at the situation 1, which is placing low power device upstream of the processor. So, if we want to keep the low power device upstream of the processor, then there is no preheating coming into the low power device. So, with that we know that there is a thermal interface material and there is a heat sink associated with the low power device. Adding those two gives me this should be 778 and a total resistance of 0.98 degree C per watt. Then using this we can calculate the inlet temperature is given as 45 degrees Celsius. So, with that so this is the inlet temperature and this is the temperature rise obtained from this, that is essentially 0.98 times 48 watts gives me the delta T, and that is 46.9 degree Celsius, and that is what this is. So, the junction temperature is 99.9 degree Celsius and it is much less than the 120 degree maximum that is allowable for the low power device. This is the low power device junction temperature. Now, we need to calculate this for the processor. What happens is, now we need to estimate first the temperature rise that comes to the processor. First we need to figure out what is the ambient temperature that comes, because there is a low power device that is placed upstream of the processor. So, that device dissipates 48 watts. So, using energy balance m dot C sub p, we know the temperature rise across the low power device plus the ambient temperature 45 degrees Celsius. So, m dot is known, Cp is known, this is 0.0116, Cp is 1006. So, we can calculate this to be 49.1 degree Celsius. So, this is the ambient temperature to the processor, assuming that the flow after the low power device is well mixed. This is a assumption that we are making. In many cases the flow may not be well mixed after the low power device. So, we will just assume that it is well mixed for the purpose of this calculation, and we know that there is a TIM for the processor, and then we need to add the processor heatsink resistance, and that turns out to be 0.264 degree C per watt based on our calculations. And so, using this resistance and this ambient temperature, local ambient temperature, we can calculate the junction temperature of the processor, and we are given already the RJC, that is the junction to case resistance, is also provided, times the power of the processor plus RTIM plus RHS plus 49.1 will fetch us the junction temperature of the processor. And substituting all these values which are already supplied gives us 103 degree 0.7 degrees Celsius. And if you calculate, because we are interested in figuring out the case temperature, and the case temperature if you calculate by subtracting the RJC value, then you will find that RJC is nothing but, it is already given, RJC is 0.1 and the power is 150 watts. So, you have to subtract 15 degrees from RJC time 103.7 minus RJC times proc gives me 88.7 degrees Celsius. But the problem states that this cannot exceed 85 degrees C. So, this exceeds 85 degree limit. That means placing the heat sink or the low power device upstream of the processor is actually going to make the processor hotter. So, it will indeed reduce the reliability of the processor. So, we cannot place the low power device before the processor. So, now on similar grounds we can calculate what happens if we put the low power device after the processor, that is downstream. So, if we use the same calculations and the same procedure, then you find that the junction temperature of the low power device happens to be slightly higher. So, one has to account for, before calculating this junction temperature, there is a temperature rise on the air side because the processor dissipates 150 watts into the airstream. So, that junction temperature needs to be calculated, and the case temperature for the processor, if we calculate using the same procedure, then it turns out to be 84.5 degrees Celsius, which is less than 85 degree, the maximum that is. So, it is best to put the low power device downstream of the processor rather than upstream of the processor. So, what we have looked at in these problems is that we looked at some simple problems beginning with a simple device that is dissipating heat on both sides. Then we went to a slightly involved problem of, okay, what happens if I put a mold, even though the thermal conductivity of the mold is poor, having the mold helps in dissipating because it provides higher surface area for heat dissipation compared to having no mold. And then we looked into a problem of high dissipation through microchannel type architectures. Even there we found that if the power levels are high, it is best to spread the heat to a larger base and dissipate the heat than dissipate the heat at a local heat source level. And that's why in many occasions providing a heat spreader is one of the best solutions in the electronics industry. So because the heat fluxes are so high, it is better to reduce the heat flux and dissipate it over a larger surface area. Following the two discussions, finally we looked at a placement problem, that is whether to put a device before a high power device. Is it advisable to put a low power device before the high power device, or is it better to put a device after the high power device? In many of these situations, we use some simple calculations and use thermal resistance network, and that helped in solving the issue. But in reality, the problems in electronics is much more complex, and often CFD, computational fluid dynamics software packages are quite often used to understand the implications. But nevertheless, having these type of simple calculations helps in doing a layout, quick layout design, and helping the designers well ahead of time. So the last but not the will look into in many occasions, for example in laptops, there is no headroom for placing a heat sink on top of a processor. Most of the time the heat is carried from location A to location B, and it is dissipated at location B where there is enough room to mount a heat sink. And so that is called the remote heat sink concept, and this remote heat sink concept is often enabled by what is called heat pipes. And in the next module, we will just look into what are heat pipes briefly, and then we will solve a quick problem at the end.